Okay, what's the limitations of B-trees? B-trees are not perfect. That's why a variation was created to solve these limitations. So, well, the first problem is elements in all nodes store both the keys and the values, right? And because you store the key and the value in every single node, then you can only store so many elements. Because let's go back here and see. Here's why. If I'm reading this node, right? If I'm reading this node or this page, because they are effectively the same thing in a database, then you're going to pull keys 4 and 8 and their corresponding values. So if you're searching for the key 1, you really just used the key, you didn't use the values. So you wasted precious memory space that you didn't really use, if you think about it. So alternatively, if I'm storing the values in the page, in the node, then these values are not just this could be up to 64-bit. So, or some people store GWIDs. So think twice when you create an index on a UUID or a string, because that puppy exists right here, right? Like if you create, for example, a primary key, right, on a string field, then this string values are stored on everyone. B+3 store them in a leaf throw, which we can discuss, but they are stored, and when they are stored, they take more space. More space means I can fit less elements in a page or in a node, and if I fit less element, that means I need to read more, right? Because I need to put more nodes. More nodes mean more pages. More pages means more IO. More IO means slow. So that's the trick here. Elements in all nodes store both key and value, so they take more space, thus require more IO and can slow down the traversal, right? So that's the trick here. So we might say, well, what else? If you don't store the value, you need to store the value at some point, right? Well, we're gonna talk about that. Another limitation of the B-tree is range queries are slow because of the random access, right? Because you're jumping and back and forth. If I ask you, give me all the values between 1 and 5, and we're gonna show you an example in a minute. Then we're gonna jump all over the place to find 1, and then find 2, and find 3, and find 4, and then find 5, right? I have to do 5 different traversals to find these values. Not necessarily, it might be a little bit less if you were lucky, but that's what I need to go. It's almost random, right? Despite them being very tucked next to each other. The keys, right? Give me all the, should be keys, not values, but you get my point. I'm searching for these values, these keys effectively, right? But B+trees solve both these problems. Another problem with this is like it's hard to fit internal nodes in memory when you have all these values, right, in each element. Because you have all these values, then I can't really fit stuff in memory, especially like, I don't know, if I have like a primary key on a UUID field or on a string field, right? Then it becomes very expensive to store this index or this B-tree in memory because it costs a lot, right, to traverse. Let's take an example of why B-trees can be bad for range queries. So I'm gonna now find all the rows ID between 4 and 9 in this particular B-tree. So I'm looking for 4 and 9. I want to pull all these rows so I can look up Pete, Edmond, Ion, Edmond, Sarah, and so what I'm gonna do is, okay, let's search number 4. Oh, we were lucky, we found number 4. Okay, let's find number 5. Where is 5? Well, 5 is between 4 and 8, so we jump to this data pointer, a child pointer, and find to this page page pointer and get to 6, or well 5 is actually less than 6, so let's jump another IO, so 1 IO, 2 IO, 3 IO. We found 5. Okay, let's go ahead and find 6. Well, 6 we just actually read it in a minute ago, so it's in memory hot, right? Unless we had to throw it back into the disk for LRU reasons, least recently used cache, like if we throw it back, but it's there. Okay, we found 6. So how about 7? Go and find 7. We found it. All right, how about 8? 8 is, oh, there you go, it's up on the road. How about 9? 9 is in this side. Go here, we read this page, and then go on, and then to the left. This is 9, and then we find the value of 9. So look at what we have done to find this, and you might look at this like, oh, it's not that bad, but we thrashed the index to look for these 5 values. Despite them technically being next to each other, they are sorted. They are next to each other, right? And that's another thing that B plus trees solved. Another thing B plus tree solved is like, it tries not to put values in these kind of hot searches. It tries to make this as slim as possible to search, and pushes all the data to the leaves, as we can see in the minute.